Hello, hello. Today we are going to talk about the tangent. So get out your 3.8 notes and we're going to talk about sketching a tangent and finding its period, amplitude, and all of those things. Okay, so let's take a look at how we're going to do this. We're going to do it along the same lines as we did the sine and cosine. We're going to just look at some values, see if we can figure out what's happening. Okay, so look, not with that marker. So let's think about just from 0 to pi, or pi over 2. Just from 0 to pi over 2. And let's remember that tangent, by definition, is y over x, sine over cosine, basically. Okay, so let's look right here at our pi over 4 angle. What do we know about the tangent at pi over 4? Well, you already know this. We've already answered this question. At pi over 4, the x and y values are the same, so the tangent value is 1. Now, what happens in between 0 and pi over 4? Well, let's look at these, just different angles in there, one of which is pi over 6, I know, but there's lots of angles in there. What is happening to the slopes of those little radius segments that I drew in there? Compare this slope to this slope to this slope to this slope. Well, isn't this slope bigger than all of them? And in fact, at this radius, which is the point 1, 0, the slope is actually 0. It's a horizontal line. Tangent is slope, y over x. So the slope from here to here goes from 0 to 1. So in other words, it is increasing between here and here. Now, what's happening between pi over 4 and pi over 2? Well, if you consider some of these segments, my goodness, it's still increasing. It's getting bigger, steeper, bigger slope, steeper and steeper and steeper. Until finally, what happens here? This is the point 0, 1, and what's the slope? Undefined. Because what kind of a line is that radius? It's a vertical line. And the slope of a vertical line we know is undefined. So let's see if we can put this in a picture. So here's pi over 4, and we said that slope was 1. And here's pi over 2, and here's 0, we said that slope was 0. And at pi over 2, we said the slope is undefined. Undefined is expressed as a vertical asymptote. So your tangent function has a vertical asymptote at pi over 4. And it is increasing, I'm going to point a little bit, it is increasing at an increasing rate. Increasing at an increasing rate. And before you question that, stop and think about it. Between 0 and pi over 4, we went from 0 to 1 in terms of slope. Slope 0, slope 1. In between pi over 4 and pi over 2, we went from a slope of 1 to a slope of infinite. So it's really, really shooting up there, increasing at an increasing rate, concave up. Now, let's look at down here. Let's look at this half of the circle. So this would be negative pi over 2. And again, right here at negative pi over 4, my slope is what? At negative pi over 4, that slope would be negative 1. Y and x are the same, but y is negative. So negative 1. So that slope is negative 1. Now, what's happening in here? Well, aren't the slopes decreasing? They're going from 0, and they're getting less and less and less and less all the way down to -1. But then what happens here? Well, they're getting really steep, really super steep. Maybe this slope is -2, and this slope is -8, and this slope is -53. And then what happens at -π/2? Well, again, at -π/2, the tangent is undefined. The slope is undefined. That's a vertical line. So there's an asymptote at -π/2. And when we connect the dots that we have, we see that we have a little concave down curve, because what's happening to the slopes? They are decreasing at a decreasing. They are decreasing very, very steeply. So as we draw this curve left to right, my curves are, my slopes are increasing, going this way now. This is how I have to look at it, left to right. As my slopes, as I go left to right, my slopes are increasing, but at a decreasing rate. When I get to 0, my slopes are still increasing, but at an increasing rate. As I move away from the asymptote, my change is less. My rate is less. As I approach an asymptote, my rate increases. So once again, left to right. Here, my slope, my tangent, my curve is increasing at a decreasing rate. It's getting closer to 0, a slope of 0. But at 0, then all of a sudden it keeps increasing, but now it is increasing at an increasing rate. Okay, now what happens on the rest of the circle? Well, if I went from π/2 to pi, could I make the same argument I made over here, starting here with 3π/4, and the slope there is -1, and at pi, the slope, and I keep saying slope, but remember, slope is tangent, they're the same thing, so the tangent at pi is 0. So the curve is coming up like this till it gets to here. And then down here in this quadrant, I can do the same thing. Here's 5π/4. And that tangent's +1. And then at 3π/2, I'm undefined again. Down here, that's actually the same as -π/2. And then the same thing would happen here to this point. And it would keep going on and on. So that's your tangent. So what are the characteristics of the tangent? If you look in your notes, each time, key concept, each time that the vertical ray is vertical, that's this, the radius, we see an undefined slope. That means in the graph, every time we're undefined, and that happens here and here, you're going to have a vertical asymptote every single time. You're going to have a vertical asymptote. Down at the bottom of the page it says, if you have the equation written as we've been writing them, but now it's tangent, this, we can't really call that amplitude anymore, because the tangent curve doesn't have a height. So there can be a number out there, but what do you think that number would do? For example, if I put a 2 out in front of my tangent equation, what do you think it would do to this picture? Well, it would vertically dilate. So it's going to multiply all of your y's. So instead of this point being up 1, it would be up 2. And this one would be down 2. Now, that isn't going to change the asymptotes, but what it is going to change is kind of the steepness of the curve. So it doesn't change the height. Tangents have no height. The A value is simply going to change its steepness. Okay? Now, if A happens to be negative, that can happen, then the curve, instead of rising, instead of increasing, the curve would decrease, get turned upside down and decrease. So A can be there and it's an important number, but you can't think of it really as amplitude anymore. All right, period. Now here's a fundamental difference between the sine, cosine, and the tangent. Remember, a period is one full cycle. And if you look at this thing that I've drawn, I have an asymptote at negative pi over 2 and pi over 2, and one of these squigglies in there, okay? Then, between pi over 2 and 3 pi over 2, okay, again, vertical asymptotes and a squiggly. So isn't this right here a period? Because isn't that a full cycle? Once I've drawn this, haven't I really drawn my curve? Because everything else is just going to be a repeat of that. On and on and on and on. So, big difference. The period of the tangent is pi. The standard period is pi. Negative 1/2 to positive 1/2 pi. So when you are finding the period of your tangent curve, the period of your tangent curve will be pi over b, not 2 pi. It's 2 pi for sine and cosine because that is their standard period. For tangent, it's pi over b. This represents the same thing as before. That's your phase shift, horizontal translation. So if it's x plus pi over 4, then you're going to go left pi over 4. If it's x minus pi over 6, you're going to go right pi over 6. That doesn't change, nor does the vertical translation, picking the whole thing up. What that would do is, instead of these points, these are on the x-axis, this is where these are like the points of inflection, where the curvature is changing, concave down, concave up. Those points would be up wherever. So if you're moving it up 2, then those points of inflection would be up here on your midline at 2. All right, so let's look at example 1. He's drawn a picture for you, and your job is to find A, B, and D. Now, clearly, there's been no phase shift. It's not even indicated in the problem, because notice your curve goes right through the origin, which is how it's supposed to go. But what do you notice that's different about the picture? Well, first of all, where are the asymptotes? Well, the asymptotes are at negative pi over 4 and pi over 4, which means the period of the picture that's drawn is pi over 2, negative 1/4 to positive 1/4. Asymptote to asymptote is a period. I I just erased my regular tangent, but you've got it here in your notes. A regular period in a tangent, regular tangent, is pi. This period, negative pi over 4 to positive pi over 4, is pi over 2. So, if pi over 2 equals pi over b, then clearly my b coordinate must be 2. Now, A is a little trickier with tangents than it is with sines and cosines. I want you to look at the picture that he drew and notice, okay, here's my asymptote at pi over 4. And here's my branch of my curve. Halfway in between there would be pi over 8, in between 0, the origin, and pi over 4, got the middle there. And notice, doesn't it look like that middle point is about at 1? You can't tell exactly, but isn't it about at 1? So therefore, there's been no vertical stretch, no dilation. Remember, in the original, in the regular tangent curve, had an asymptote at pi over 2, and halfway between 0 and pi over 2, the slope was 1, right? So if that slope at that halfway point is still up 1, approximately up 1, then A is 1. A is 1. If that point, let's say that point had been up here like this. So now that middle point, that 45-degree angle in a regular unit circle, if it's not 1, if it's something else, then that tells you that your A is in action. So this A would be 2, because that middle point between 0 and your asymptote is supposed to be at 1. If it isn't, then you got to figure out how it's changed. In this case, it's been times by 2. So that would have an A of 2. The one on the page has an A of 1 because that point at the halfway is exactly where it needs to be. Okay, and there is no D because the points of inflection are still on the x-axis. These points right here, I didn't draw the rest of my picture, but these points right here are still on the x-axis. So we have not had any kind of vertical translation. So A is about 1. I can't tell exactly, but it looks like it's about 1. B is 2, period change, and D is 0. There's been no vertical shift. Okay, example 2. Now we have this function. And all you're figuring out is the period. So easy. What's period? For a tangent, period is pi divided by b. Well, b is 2, so the period is pi over 2. Just for fun, let's graph that, get a little practice. He doesn't ask us to do that, but we're going to need to know how to do this anyhow. So let's graph that thing. Okay, first thing I notice is I have a midline at 5. So now remember what that means. That means that your curve is going to change concavity on that line instead of this line. Okay. Second of all, I'm going to notice that there's been no phase shift. The tangent is 0 is 0. So there's going to be one of my points right there. On either side of that point, someplace, there's going to be vertical asymptotes because that's what a tangent looks like. The distance between those asymptotes is the period. This is 1 period. Well, for this problem, I know my period is pi over 2. So I need to go from my origin origin point, I need to go this way and this way the same amount. Well, if the whole thing's pi over 2, then when I go pi over 4, negative pi over 4, and if I wanted another one, because remember, it goes on forever, what would this asymptote be? Well, again, asymptote to asymptote is a period. So if the period's pi over 2, then this would be 3 pi over 4. And you could draw as many as you wanted to. Okay? Now, halfway between these asymptotes are these, what we call zeros. Only they're not going to zeros anymore because they're up on this line now. And that's where my concavity changes. Now, in a normal tangent curve, the halfway point between 0 and the first asymptote would be up 1. So it would be at 6. Again, that comes back to that. If you're looking at your unit circle, the halfway point is pi over 4, and the slope at pi over 4 is 1. So, halfway between, and you don't need to label it, but halfway in between 0 and pi over 4, it should be at about 6. Okay, so it should be up 1. Well, look what we've done. We've times that by 4. So this point, instead of being up 1, it's going to be up 4. So it's up here now at 9. So this curve is very steep. And similarly, identically, on the bottom. Very steep. And then the same exact thing would happen over here. Very, very steep curve. The only thing I haven't done, I don't need to label this point, that's 0, but I do need to label this one. What is halfway in between pi over 4 and 3 pi over 4? That would be 2 pi over 4 or pi over 2. And there we go. Didn't quite make that one steep enough. There we go. Okay, there's 2 periods. I graphed 2 periods of it. You'll get the hang of it. You'll get the hang of it. All right, example 3. Which give the vertical asymptotes of this curve? All right, let's take a look at it. All right, we're going to sketch this one too, just because I think we need to practice. Now, this one's going down 1. That will have no impact on the vertical asymptotes, but since I'm drawing it, I'm going to go ahead and talk about my midline now is down at -1. That means that these points of inflection are going to be on this line now, this time. I notice that once again, I have no phase shift. So that means my 0 stays the same. It hasn't been shifted left or right. So I'm going to have a dot right here. The one that's at the origin. Again, keep in mind what a regular tangent looks like. Okay, that dot is still there. I've done nothing to move that dot, except down 1. Okay? Now, what's my period? Well, my period is going to, think of this as 1/3 x. So my period is pi over 1/3 or 3 pi. Now, what does that mean? That means that between this vertical asymptote and this vertical asymptote, that distance is 3 pi. That point splits the difference, it's right in the middle. So if the whole thing is 3 pi, then this would be half of that, and this would be half of that. In a perfect world, right here in this first, I call it first quadrant, this little first section right here, I would go over halfway and up 1, so that point should be right there. The middle of this, the point that's in the middle of these two, should be up 1. But this one has been times by 2, so that point is actually up here. And this is the same thing but negative. So now I can sketch in my curve. See how easy it is? Now, I forgot what the question was. The question was, I need the vertical asymptotes. Well, keep in mind, it does go on forever and ever. So the answer isn't just negative 3 pi over 2 and 3 pi over 2. Where would the next asymptote be? Well, remember, the distance here is 3 pi, which is 6 halves. So the next one's going to be at 9 halves. And the next one will be at 15 halves, and so on and so on and so on. So which one of these things expresses that? Well, first of all, we see the 3 pi over 2's, and we can either add 3 pi to that or subtract 3 pi. What variable are we using? K, where K is now, he says a constant, which is true, but we need it to be a whole constant. We need it to be a whole number. Because we're going to take 3 pi over 2 and either add 3 pi's or subtract 3 pi's to generate those asymptotes. All right, example 4. What are we doing here? Which of the following could be an expression for K? So in other words, we need an equation for K. First thing I want you to notice, I hope you notice when you look at that picture in example 4, it looks like the points of inflection are at -2, which means your midline is at -2. So we can automatically rule out B and D. B and D are ruled out because we're dropping at 2. All right? Another thing I hope you notice is we got a period change here. The period, asymptote to asymptote, the period is 2 pi. And we know that period is pi over b. So 2 pi b equals pi, and it looks like b has to equal 1/2. So that would be equation A. Remember, tan x over 2 is tan 1/2 x. So the answer is A. We have a vertical translation of -2, and we have a horizontal dilation by a factor of 1/2. Okay. Find the values of the expression using the unit circle. All right. Absolutely, positively, you can do these problems. They were on your quiz. You know how to do these problems. So you can just go ahead and do those. I don't think we need to do it. I want you to do it, and we will check those to make sure everybody's on target in example 5 the next time we're together. All right, I want you to skip page 3. If we were together, we'd do some of that, but we're not, so we'll go straight to page 4. And we're going to do the check your understanding. Now, here's the deal, folks. The question says, find an exact value for the slope. That's like find the exact value of the tangent. So we are finding the tangent of 7 pi over 6 and the tangent of 5 pi over 3. Okay? So I always have to visualize it. Here I am, 7 pi over 6. It's a pi over 6 angle, but it's in quadrant 3. So that would be negative root 3 over 2, negative 1/2. Slope is this one over this one. So negative 1/2 over negative root 3 over 2. Negatives cancel, 2's cancel. 1 over root 3 or root 3 over 3 for our slope of 7 pi over 6. 5 pi over 3 is over here. It's a pi over 3 angle, so it is in quadrant 4. So it will be 1/2 root 3 over 2. And the negatives, root 3 over 2 is negative. So tangent is going to be y over x. So that's just going to be negative root 3 over 1, negative root 3. Next question says, explain why the tangent is always increasing from negative pi over 2 to positive pi over 2. Well, this is easy, guys. What's the slope down here? Undefined. But it's undefined because these numbers are getting, as you get closer to that, the slopes are getting bigger and bigger negative. So the slopes are actually like negative infinity down here. And then as we move toward pi over 2, they're going from negative infinity to positive infinity. That's why they're increasing. Negative infinity to positive infinity. All right, consider this one. It looks like one we just did, maybe. The graphs, we're gonna do the graph and then we'll be done. So let's answer the questions, get the graph done, we're ready to go. What transformation occurred from the parent function y equals tan theta? Okay, so consider the regular curve, and then look at this one. This one is going to have a period of 2 pi, so it's actually been stretched. It's a horizontal, the number, the B number is 1/2, but remember it's really divided by 1/2, which is timesing by 2. So we have a vertical stretch, a horizontal stretch by a factor of 2. The period's 2 pi. Where are the vertical asymptotes? Well, this equation has no horizontal shift, no phase shift. So your 0 is still at 0. For a tangent, guys, the 0 is going to be at 0 unless you move it. And the only way to move it is to slide it left or right. And the only way that happens is if you do something like this, okay? That would move it. But I don't have that, so I'm not moving it. So I know I've got a 0 at 0, and on either side I got an asymptote. And the distance between those asymptotes is a period. That does not mean 2 pi, 2 pi. It means here to here is 2 pi. So here to here would be pi and negative pi. So on your graph paper, put an asymptote at negative pi and positive pi. Put a dot at the origin. Now, halfway between that would be pi over 2. Your dot should be up 1 because you do not have any kind of vertical dilation. Other way, down 1. So that would be at negative pi over 2. So plot the point, pi over 2, comma 1, and negative pi over 2, comma negative 1. And then just draw in your squiggle. Now, yours is going to be a lot wider because this graph paper is wider, but you should have an asymptote at negative pi, an asymptote at pi, a 0 point of inflection at the origin, and then at pi over 2, halfway between, at pi over 2, 1, and down 1. All right, that takes care of that. I'd like you to spend some time with your 3/8 homework. Also, make sure that you finish notes example 5. We're going to check those. Make sure that you are on target with your tangents. Thanks, guys. Have a great day.